Right, this is the third part of Unit 7, where we are going to look at constitution and geometry. And basically, constitution means just what is the coordination complex made up of. So how the ligands are arranged around the central metal atom. And we generally refer to that as coordination number. And obviously then what geometry it's going to produce. Most of the geometries you're familiar with already because you've done bonding geometries and they're pretty much the same. But these coordination numbers are going to be affected by the size of the central atom or ion, any kind of steric interaction between ligands, in other words, how bulky are the ligands, how big are the ligands, and do they fit in the space around the metal. And then, of course, some electronic interactions between the central atom and the ligands themselves. Let's start with the simplest coordination number, which is coordination number 2. It results in linear geometry, and it's mainly found for the elements for copper 1, gold 1, mercury 2+, and silver 1. And it's simple really, it's just two ligands attached to the central metal atom giving you linear geometry. Coordination number 3 gives you a trigonal arrangement. Okay, these are not very common, but they are seen for very bulky ligands. For example, triphenylphosphine is one of them, and the other one is tricyclohexylphosphine. The example of which is shown to you on the slide over here. Okay, you have, this is actually the ligand group. Let me just draw it around it for you so you can see that is the ligand. So you can see it is tricyclohexyl. These are the cyclohexyl groups over here and over here, over here, and obviously on the other side as well. And they are exceptionally bulky ligands. And generally you would find that most of the MX3 complexes would have this type of trigonal arrangement. If we look at coordination number 4, you know that you're going to get a number of different geometries, the most common of which is the tetrahedral complex. Okay. For certain metals, you will find that you will get something called square planar. Okay, so you have the metal in the center over here, and the ligands are arranged in a square type geometry like this in the plane. Okay, and a typical example is given here of zinc porphyrin, and this is what zinc porphyrin looks like. If we move on to coordination number 5, the most common geometry of which you're familiar with is the trigonal bipyramid, and we also get something called square pyramid. Now, what happens with a trigonal bipyramid is that sometimes it can move and rearrange itself to become a square pyramid. Okay, so if we look at this example that's showed on here, this rearrangement is called Berry pseudo-rotation, and you'll see that in diagram A over here, you have your typical trigonal bipyramid. Okay, and what tends to happen is that suddenly you have a shift of the various atoms. So the orange atom is going to shift to this position here. The blue atom is going to shift to this position up here, and you'll end up with, in diagram C over here, you'll end up with a square pyramid. It doesn't look very square pyramid at the moment, but you will actually just see that you can actually draw a square from here to here to here like that, and you have the pyramid on the top. And a typical example will be of this complex shown on the right hand side over here. Right, coordination number 6 is mostly octahedral or distorted octahedral. So this is what the octahedral complex looks like. Okay, the diagram in the center shows all of the symmetry elements that you can see. Okay, you will see them labeled here. There's a C4 rotation, C2 rotation, and even an S4 rotation. I'll remind you to go and revise what those things mean. And you even see the mirror planes. So you'll see there's diagonal mirror planes and horizontal mirror planes, all relevant. I don't expect you to know those because octahedral geometry is quite high symmetry, but I just need you to know the arrangement of the atoms around the central metal. So here is the central metal, and you know that there are 6 arrangements of atoms around coordination number 6. Okay, you can see how distortion can happen. All right, so we can get the 2 axial points. So this point here and this point here can be squashed inwards to give us a distorted octahedron. Those same 2 points can be pulled apart in diagram B. So we have a pull apart this direction and pull apart this direction, and you'll have a distorted octahedron. And then you have other ways of happening where you have four distortions as shown in diagram C over here, and then you also have this sort of sideways distortion in diagram D. Molecules and coordination complexes tend to do this sort of thing for whatever reason, outside influences, physical effects, temperature effects, etc., etc. Okay, for the octahedron or the distorted octahedron, the chelating ligand that will allow a small bite angle can distort the octahedral complex into something called a trigonal prism. Okay, now if you look carefully, you will see what happens is you see in this diagram on the far left at the bottom, you'll see what a trigonal prism looks like. What happens is that it starts from position 1 here, and this atom, and this atom here simply rotate to be in alignment with the orange atom. So the green one, this one will move so that it's pretty much in line with the orange one over here. You can see how the distortion goes until eventually you end up with the orange atoms in the third diagram here. So this is diagram 2 and this is diagram 3. Okay, you can see how the positions keep moving until you end up with this being the octahedron here and this being the trigonal prism over here. Right. What about the higher coordination numbers? And you're saying to me, Dr. Ardern, is there actually higher coordination number than 6? And I say, yes, there is. There are 2 more. Coordination number 7 and number 8. Okay, so most of these high coordination numbers will occur for the F block elements because the metals themselves are very big, and to accommodate so many ligands has to be done for these metals with their F orbitals. So these metals have F orbitals, and for them to accommodate, they can accommodate many more ligands around them, and you'll end up with very different geometries. So you'll end up with something called a pentagonal bipyramid, which is this example here. You end up something here with a capped octahedron, which is this example here. You then also get a capped trigonal prism, and you also get a square antiprism. Okay, so that's for coordination number 7, and a typical example is given to you in this diagram over here. And then lastly, you will have coordination number 8, again also applying to F block elements, where you get the dodecahedron, and it looks something like this. In this diagram here also you get a cube. Okay, so the coordination numbers for all of your cubic structures, your ionic structures that we learned about in unit 3, your structures of simple solids, the cubic structures, In this example, you should be able to recognize the body-centered cube, and you will see that some typical examples are in this case for the octacyano molybdate ion here. This example, you've got to remember how to name them. I've been teaching you how to do that in the previous part of this unit. And you will see here is another good example at the bottom of an 8 coordination. If you count the number of bonds, so you've got 1, 2, 3, 4, 5, 6, 7, 8. And that kind of concludes this particular part of coordination chemistry regarding constitution and geometry. And we'll move on to now the last part, which will be isomerism and chirality.